Welcome back to this course on Fundamentals of Computer Architecture. In this lesson I will explain how the performance can be summarized when there are several benchmarks. Let's turn to the question, how do we summarize performance? If there is only one program that is executed on several different computers, it is clear which computer is faster. When there is a collection of programs, however, things become kind of tricky. How do you aggregate or summarize their performance? Let's look at this example. Here we have two programs, P1 and P2, and three computers, CPU A, CPU B, and CPU C. Program P1 takes 1 second on A, 10 seconds on B, and 20 seconds on C. Program P2, on the other hand, takes 1000 seconds on A, 100 on B, and 2 seconds on C. In total, therefore, programs P1 and P2 together take 1001 seconds on A, 110 seconds on B, and 40 seconds on C. This is all plain and simple, but what if the programs are not run equally as often? What if, for example, we run program P1 10 times as often as program P2? How do we summarize performance then? Then there are basically two approaches. The first is to use the weighted execution time. The second is to normalize the execution times to a reference machine and then take the average. To calculate the weighted execution time, each program Pi is given a weight I, that indicates its frequency, the number of times it is executed divided by the total number of program executions. By definition, the weights or frequencies must add up to 1. Furthermore, program Pi takes time I. Then the weighted execution time is given by the weighted arithmetic mean, which corresponds to this summation here. Let's look at an example. Here we have the same execution times as before. If we now take the arithmetic mean, meaning all weights are equal and all programs are run equally as often, CPU C would be the fastest. Now let us assume that the weight of program P1 is 80% and that of P2 is 20%. Then the weighted execution times are given by 200.8 on CPU A, 28 on CPU B, and 20 on CPU C. So CPU C would still be the fastest, since in this case lower is better. But what happens if the weight of P1 is 90% and that of P2 only 10%? Then the weighted execution times are 100.9, 19, and 20 respectively. So now CPU B is better than CPU C. This example clearly shows that which computer is faster on a set of benchmarks depends on the frequency of each benchmark. Here's a question for you to test yourself. We want to buy a new computer and most of the time we use our computer to run two programs, P1 and P2. We execute test runs of our favorite applications on three recent computers, C1, C2 and C3, and obtain the results summarized in this table here. Program P1 takes 1 second on C1, 10 seconds on C2, and 100 seconds on C3. Application P2, on the other hand, takes 100 seconds on C1, 10 on C2, and 1 on C3. Now the question is, when is C1 the best buy? In other words, what should be the execution frequencies of P1 and P2 so that the weighted arithmetic mean is the least, the smallest for C1? Similarly, under which conditions is CPU C2 the best buy and when is C3 the best buy? Later in this lesson, I will provide a partial answer to this question. The second approach to summarize performance is to use normalized execution times. In this case, the execution time is normalized to a reference computer, let's say deep thought, and then you calculate the normalized execution time or execution time ratio as the execution time the program took on the reference computer divided by the time it takes on the new computer, the computer we want to benchmark. In fact, this is the method used by SPEC, and they call it SPEC ratio. But, and this is very important, you shall not use the arithmetic mean to average normalized execution times, for it can lead to different results depending on the reference machine. Because it is so important, I repeat, you shall not use the arithmetic mean to average normalized execution time, for it can lead to different results. To warn you once and forever, here's an example of this wrongdoing. Again, here's our example from before. Two programs, P1 and P2, that are executed on three CPUs, A, B, and C. If we now normalize to A, so take A as our reference computer and calculate the arithmetic mean, we get these results. C is the fastest because its arithmetic average is the largest. Now, if we normalize to B on the other hand, we get these results. Suddenly, A is the fastest since it is 10 times faster than B for program P1 and 10 times slower or 0.1 times faster than B for program P2, corresponding to an arithmetic average of 5.05. Clearly, something is wrong here. But what can we do then? What should we use instead? We should use the geometric mean instead of the arithmetic mean. The geometric mean is given by the nth root of the product of all execution time ratios. The geometric mean is independent of the choice of reference, as this example here shows. In all cases, C is the fastest computer, independent if we normalize to A, to B, or to XYZ for that matter. This completes this lesson. Thanks for watching. In the next lesson I will describe the CPU performance equation, which is one of the few equations in computer architecture that you should know by heart. Hope to see you back.